Good morning, y'all. Welcome back. This is Engineering 11. We're doing Intro to Matlab. Today we're going to finish up Lesson 4, which is all about storing and manipulating signed integers. Natalie had a beautiful question last time, which was, hey, Jeff, do you have Lesson 4 suggested problems copied? My answer to that question is yes. They are in the box now. There's no label on them, but they're right behind Lesson 1, Part 3. Would you like me to make copies of the prompts for suggested problems Lesson 2 and Lesson 3 as well? Okay. I'll have those ready for you next week. Are there any other questions that you think that I should address before we launch into the other parts of our work today? Oh, yes. Thank you so much. So, yes. So, exam discussion. At end of lecture. So let's say somewhere approximately like 11:40 a.m. And why don't I just go ahead and set my alarm to shut up, right? Okay, so that addresses that question? Yeah. Thank you so much. That's a beautiful question. Other questions that you might have for me about how the class is functioning or stuff that's come up? As they come up, remind me. Let's get started with our review from last time. So where did we end last time? We won't spend too much time on this, but in Lesson 4, Sessions 1 and 2, we introduced the idea of signed integer representations. Do you remember the two names of the signed integer representations that we worked with? Yeah, go ahead. Yeah, we had something called the sign magnitude representation. Of, let's call it y in z. And for now, let's go ahead and think about the last time that we did it together, we actually did m is equal to 7, I believe, right? So we did an 8-bit encoding. Let's see if we can abstract away from m equals 7 and do it in general terms. This is going to be a binary encoding, but this is not unsigned integer maps. This is what we're going to call the sign magnitude map. What is the corresponding decimal representation of that map? Yeah, one thing that we could do actually is we could actually do like a kind of a bit map. So if we're going to think about this as, perhaps we call this bit number. I don't really want to call it bit number. I think we should call it position number maybe. Yeah, that's maybe a better way to do this. So position number. The most significant bit, let me ask you this. How many bits are used in this encoding? Yeah, I agree with you. If m is 7, then the encoding is 8. Yeah, okay, so this is what we're going to call an m plus 1 bit encoding. The most significant bit, so we'll call that kind of like MBS, but very different. Most significant bit. What's the position number on the most significant bit? M. And then what we'll kind of do is to map these ones without a hard delimit line. What would be the position number of the least significant bit? 0. The second least significant bit. And then all the way down to, I guess I'm running out of room here, m minus 1. We had this really, really special thing when we were talking about the signed integer representation. And I suppose I need someone with an artistic flavor. I need 2 colors. Yell them out. But not all at once. Red and blue? Awesome. All right, maybe we'll call the most significant bit, we'll do in red. Does that sound okay, Adam? And then we'll do this entire thing here in blue. Why am I grouping the m least significant bits together? Another way to ask that question, let's call this page 2. We indeed, what's the day today? Wednesday the 5th, my God. Too fast, right? So this is going to be 10:07 a.m. All right, so let's think about this for a minute. What's the corresponding map if I want to map this thing back into decimal numbers? So here I've got this thing b sub m. Here I've got this bit b sub m minus 1, b1, b0. What do I do with the leading bit in the sign magnitude? Yeah, I take -1 to the power of that bit. That whole value, maybe I'll do this in red, since I'm going to follow my friend Adam's suggestion here. What do we call that? Every number in this representation has both a and a magnitude. This thing right here represents the sign. Then what we do is we take that sign and we multiply it by the corresponding magnitude. What would be the magnitude in this case? Well, the claim is that all the work we did in unsigned integers, we just immediately steal that work again, right? So from this standpoint, all the stuff in blue, that thing is called the magnitude. We will come back to this. The reason that I actually wanted to do this, even though Matlab does not use this representation for signed integers, the IEEE format does actually have the exact same idea in the sign bit. So this idea is going to come back later. And then the second thing is 2's complement magnitude is unintuitive enough that we might want to know why would we ever mess with 2's complement if we could just encode it like this. So let's make the note again. Sign magnitude representation is a useful, perhaps we say, gives an intuitive introduction for doing what? What's the major idea in the sign magnitude representation?
The first bit represents the sign.
Yeah, can we use the word most significant?
Most significant.
Awesome, cool. Only because, yeah, so using the most significant bit, to encode signs. And let's go ahead and write a piecewise function there. So if I say that my most significant bit is B sub m, what are the two choices that I have for any binary digit? 0. Yeah, so this correlates with a positive sign if the B sub n is 0, and a negative sign if B sub m is 1. And that indeed will be a theme that we return to the entire time. But Matlab does not use sign magnitude. Do you remember the reasons that we gave that it doesn't use sign magnitude? There were two of them that I'm going to focus our mind on. Yeah, go ahead, Taylor. Yeah, because A, there is a poorly defined 0. And then B, sign magnitude actually would need new circuitry to do addition / subtraction. Because the idea is that I would have to actually check the magnitude, I have to have if-else conditions, etc., right? So, I mean, this is not clear. This is written in like, what is this, like a minute we talked about this? This took the computing world like, I don't know, 15 to 20 years to recognize that this is not the most efficient way to do signed numbers. So let me not say that like, oh, just because I'm saying this, you should be clear to you all. It's not until we were actually to try to code this up. I actually have this beautiful proposal for a grant that I don't know when I'm going to do it. I would love to have somebody pay my time out, and I'd love to work with a computer scientist to build an entirely functional 16-bit computer that allows us to do numerical analysis and lets everybody that builds the thing see what's actually going on underneath. Put the entire design online, put all the build on YouTube, and then once we have that working bit computer, encode Matlab. It doesn't even have to be Matlab. It could be any language. When you write the plus sign, what's the actual electronics going underneath, right? So that you could actually see what you're doing when you're doing it, right? As a training. Okay, so what we said then is let's come up with an alternate map to encode signed integers. What's the alternate map to encode signed integers that we used? 2's complement. And we're actually going to do, we'll do what we call an 8-bit 2's complement. We'll also do, can you guess the 4 that we're going to choose? 8-bit, 16-bit, 32-bit, and 64-bit. And we might ask ourselves, why did we choose those numbers? Well, let's just remind ourselves, what data class in Matlab does this go to? That's the int8 data class. This one would be the int16. This one would be the int. That would not be very good choices by the Matlab design team, right? And then this would be the int64. And to be honest with you, because we're doing this in general, I'm going to ask us to do something quite special, which is to do what we call the m bit, right? So if I do, we should really call it the m plus 1 bit, right? All right. Let's go ahead and think about the representation of our 8-bit, and we might actually use Adam's wonderful suggestion to us. So we'll call that B5, we'll call that B4, B3, B2, B1, B0. We're going to use the same idea here. The first bit in this 2's complement representation, what are we going to call that first bit? Or, excuse me, the most significant bit. What do we call that? Yeah, so we'll call this the sign bit. The funny thing about that sign bit, however, is that it's represented in a very, very interesting way. The rest of this thing literally goes back to an unsigned integer. So this is going to be a 7-bit unsigned integer. I don't know if I'm going to be able to do this, but I'm going to try. I want you to... Did anybody bring your Rotten Tomatoes today? Okay. All right, well, okay, get your metaphorical ones out, because I'm like running out of space here, and that's like one of my most frustrating things to do as a mathematician, is not give myself enough space on the page. What is the value if I encode these 7 bits in terms of its interpreted decimal value? B sub I times 2 to the I. What's the major condition of a 2's complement representation? What's the special thing we do to the leading bit? So another way to say this is, let's think about the corresponding value. Imagine this was an unsigned integer. What would I scale B7 by in an unsigned integer? Two to the 7th. In 2's complement, just have that scaling be negative. Which is kind of nice, right? I know what you're going to say. Jeff, this is all nice. Thank you. You're so sweet. Because we don't... What's the only thing we have to remember from 2's complement? If we get the unsigned stuff, we get 2's complement for free, as long as we remember that 2's complement is for sign. What's the only thing difference about a 2's complement versus a unsigned integer? Yep, just put a negative, drop a negative on most significant bit of unsigned map. All right, now I ask you. I'm not going to write all 16 bits out. But I am going to write the most significant bit. If this is a 16-bit, what is M? What's the most significant bit index? You said 15, right? Very nice choice of colors. You're making me smile right now. And then this would be B14 all the way down to B0. Let's go ahead and think about this map. So see if you can intuit. Yeah, so this would be negative B15 times 2 to the 15 plus I goes from 0 to 14, b sub I times 2 to the I, which is almost identical. Finish my sentence. Certainly to the previous one, but let's see if we can make the connection between this and the unsigned integer representation. Yeah, out loud. Go, keep going, Misha. Yeah. So it's now use the words most significant bit. So literally, if I know the unsigned integer, I get this one for free by just dropping a negative on the most significant bit, right? Okay. How many of you would like to do 32, or how many of you would think you're ready to do the m+1 bit? Okay, Michelle? Do you agree with that sentiment? Okay, let's do it. So let's see if we can intuit the most significant bit scalar in the m+1 bit. So we'll call this b sub m. If that's b sub m, what's the next one? All the way down to b1, b0. Anytime we're doing a signed representation, we're going to think to ourselves that that most significant bit encodes the sign, which means if it's 0, the sign is positive. If it's 1, the sign is negative, which really means if it's a active high paradigm, if the voltage in that slot is low, the thing is a positive number. If the voltage is high, it's a negative number. Opposite in architectures which use the opposite mapping. Okay. So read it to me. This bit string correlates with what value? Negative b to the m times 2 to the mth power. Nicely done, Shayon. 2 to the I. This leading thing is literally identical to the one before it. The major difference is the sign. This literally is an unsigned integer where it has 1 minus the number of bits of the total encoding, right? So I'll let you finish those other ones for yourself. In fact, hopefully on your practice you can do this. So please enjoy the pain. Oh, I know what you all are like, no, this class is super fun, Jeff. It's never painful until you finish your assignments, and then I'm like, what the All right, so let's go on. Let's start to discover what this actually means in terms of the corresponding representations. And then we'll start to do some math, and we'll see that the stuff that's done in Matlab correlates with the math that we're doing. So I think we actually talked about the idea that we could store. Oh yeah, so this is gone. Gone. Oh yeah, we talked about the idea that we could store numbers in 8-bit, right? Let's do some 16-bit examples to see if we can start getting our heads around, and then we'll do some code in Matlab as well. And why don't we do some that's just off the, so give me some negative numbers. So what's really nice about the positive numbers, so if I let y be in z, I'll be right with you. And suppose I want to capture using int 8. What's the range of y and z that are captured exactly, and then I'll be right with you. Yeah, go ahead.
So what I was going to say is that there's another way to look at between unit 8 and int 8 specifically is like unit 8, the range is from 0 to 225, right? So you're using all your bits in the positive direction. But when you go to int 8, you take that range from 0 to 225 and bring it to the left, 128, and so we have negative 128 to positive 127.
Okay, yeah, let's go ahead and write these in our different modalities. What am I going to write for my upper bound there? This thing is going to be now binary. So I'm catching up to you. I love the exploration you're doing there, Misha. How exciting. What was the other representation that we had in this class? Okay, so what's the corresponding range for a uint8 integer in hex? That's the grade I deserve on my ability to get Lab 3 prompt done. Not just one, I get two, right? But I hope that you appreciate that I'm actually trying to do something that represents my best work. And that the same flexibility that I take for myself, I've given with many of you in your lab work, right? Okay, so what you were saying, Misha, is that yeah, we're going to repeat it actively. So I'm actually going to have to catch up with you. Okay, so let's think about the same idea. We'll try to do line by line with the int 8. Okay, what is the lowest value the lower bound? So I guess we need some notation. Let's call this the lower bound. And then the funny thing is, we didn't talk about that. We'll call that the upper bound. This only makes sense in the context of a binary map. So in this map, what map have we used? The unsigned integer map, right? What's the lower bound on a 2's complement 8-bit signed integer? Well, let's think about it. If any of these things are non-zero, and this is 1, so suppose that the leading bit is 1. The moment I know the leading bit is 1, what happens to the entire thing? It's shifted down by 128, right? The moment I drop one of these to non-zero, I take a negative 128 and then add a positive number. Am I shifting left on the number line or shifting right on the number line? Right. So what's the lowest possible value? A 1 in the leading bit and zeros in the trailing bit. What value does that correlate with in terms of integers? Yeah, so negative 128 is the absolute smallest integer that I encode. I can continue to count upwards until I get to what? What would the largest integer that I impose be? Be careful, it's 8-bit. Yeah, so I would, if I got this to be 0, there would be no negative component, and then how would I max out the 7-bit unsigned integer? Put all 1s, right? What would happen if I add 1, 1, 1, 1, 1, 1 all the way down? So 2 to the 0 plus 2 to the first plus 2 to the second plus 2 to the third plus 2 to the fourth plus 2 to the fifth plus 2 to the sixth. It's 2 to the 7 minus 1. What is 2 to the 7 minus 1? 127. Let's think about the corresponding bit string. What bit string encodes negative 128? What bit string encodes this? Oh, yeah. Do you see a complementarity there? Do you see it? If I did a bitwise complement, what does a bitwise complement mean? Flip every bit. What happens if I flip every bit there? What string do I get? Yeah, in hex, so this is what we call decimal. This thing right there is what we call binary. Could you guess what the hex is? There's got to be a rap song that says what the hex is. I'm going to do it. And I'll sell exactly one copy to my wife. Yeah, go ahead.
80 to 70.
80 less than y, less than or equal to, well, let's see. 1 plus 2 plus 4 is indeed 7. 1 plus 2 plus 4 plus 8 is 15. Okay. It's very interesting, isn't it? There's a lot going on here. So let me ask you this. Let's count upwards. From the lower bound. And we're going to do this both in decimal and in binary. And you know what? I want to do a compare and contrast so that we can really get our heads around what the heck the words 2's complement means. And then we're going to make some conjectures, and then eventually today we're going to do some mathematical proofs, and we will confirm that MATLAB indeed does not deserve to be thrown away. Well, we're not sure of that yet. But I have the question, do the coders at MATLAB get to keep their job with respect to their signed integer data class? I don't know the answer to that question yet, but by the end of the day, I should be able to do some tests on their work to confirm that they are doing work. Not sure what work they're going to do. Okay, so let's start with uint. What's the lower bound in uint in decimal? 0. Corresponding binary is 4 followed by 4. And then count up for me. 1, 2, 3. I think if we went to 8, we'd see the pattern, right? So let's go to 7. 5, 6, 7. It's a nice little pattern for us. Okay, what do I do to get these ones? 0, 0, 0, 0, 0, 0, 0, 1, and then I just count up. I'm going to ask you, what's the pattern? There's a lot of repeats here, and we're going to use some colors to capture this. So now I need 3 colors. Adam, you're going to be my man today. Awesome. Michelle took over the reins. What pattern do you see in that bit string? The least significant bit flip-flops between 0, 1, 0, 1, 0, 1. Why does that make sense in terms of counting? I want you to use the words odd. Say it again. Odds and evens. When the trailing bit, when the least significant bit is 1, that correlates with an odd number. When the least significant bit is 0, it correlates with an even number. What is the second least significant bit pattern? 0, 0. 1, 1. 0, 0. Every 2. Why does that make sense? It's the 2's place, right? In these two, you don't need 2's. In these two, you need a 2. In these two, you don't need 2's because the 4 carries the most significant, right? In these two, you need 2's. What's the next one? Every 4's. Could you guess the next one? Every 8. Could you guess the next one? 16. Okay. So you're telling me that when the least significant bit is 0, the thing correlates with an even. When the least significant bit is 1, it correlates with an odd. Okay, so let's think about this now. Let's do the same thing in signed. What is the lower bound? We're going to call this lower bound. So I suppose of the entire data class for int 8. Well, what did we say it was? What's the smallest number that I can encode? Negative 128. What's the corresponding binary representation of that thing? 1, 0, 0, 0, 0, 0, 0, 0, and then count upwards. Of course, you're going to have to do the whole thing for yourselves, right? So let me ask you this. How do you think about negative 127 and negative 128? Well, negative 127 is 1 plus it's 1, a positive 1 plus negative 128, right? What's the corresponding value of 126? Two plus negative 128. Next one. So what's the pattern there? Pretty much the same, but exactly opposite, right? Because in this bit string, we're adding that value of the unsigned integer to 0, right? But in this one, we've shifted the 0 mark all the way down to negative 128, and then we're adding the corresponding value of a positive integer to move down, right? So I'll let you finish that on your own time. With this in mind, we can do this thing here. Which is to get the entire set of, yeah, and the reason that this is really interesting is check out the, what you might call I don't even know if this is wide enough to do this, is it? So if you were to do this, and could you imagine? I want you to check this out right here, and this one right here. Can you see that? What do you notice about those two numbers? Let's do some more. Let's take a look at negative 125 and positive 125. Let's keep going. We're going to make some conjectures here. Go ahead. Say it out loud. So let's write these right next to each other, right? So we got 120, positive 127. The moment I know that it's a positive, what do I know about the most significant bit? 0. And then if it's 127, that's 2 to the 7 minus 1. What does that immediately mean about the 4 trailing? Or the 7 trailing? Okay. Let's try negative 127. What's negative 127? Well, if it's negative, what does that immediately mean? Most significant must be 1. Then what? All zeros except for least, because to get from negative 128 to negative 127, that's equivalent to, say, negative 128 plus 1. That thing's kind of special, right? Okay, let's try the next one. So let me ask you, what is the bitwise complement of this string? So let's just do a quick, we're going to have something called a bitwise complement. And we'll go 0, 1, 1, 1, 1, 1, 1, 1. And let's go ahead and introduce some notation. We'll put little lines on top of a bit when we want to take the complement of it. So what's the complement of 1 with respect to 0? Flip the bit. Flip it from high to low. So every time I see a 1, I go to 0. Every time I see a 0, I go to 1. So it's not the case that this number is the pure bitwise complement, is it? So, I don't know, do you want to call this thing y?
Sure, why not?
Why not? And we'll call this thing over here negative y, I suppose, right? And then maybe we call the bitwise complement like y hat? I don't know. So let me ask you this. Negative y, what's the connection between y and negative y? What would you need to do to y hat to get negative y? Damn. Guess what you've just done? You've come up with a conjecture on how to get 2's complement number from the corresponding positive number. Right? So this is a conjecture. We have not yet proved this conjecture yet. Let's try the next one. So let's try, give me any number actually, between 0 and 127. It has to be an integer. That was really fun just now. Say it again. Say it again. An actual number that's an integer, I mean.
37.
37. Okay, so let's do positive 37. What is 37 in an 8-bit signed representation? Is it positive or negative? Positive. The moment I know it's positive, what I know about the most significant bit? It's got to be 0. Okay, and then 37. Yeah, I kind of like the way you were thinking about that. So let's do a little note here. 37 is 32 plus 4 plus 1. Okay. I would probably construct it from the least to the most. 0, 1, 2, 3, 4, 5, 6. Okay, we'll call that y. What does that immediately mean for negative y? Well, that would be negative 37. What was our conjecture? Let's use the conjecture. Let's not use our brain. Let's use the conjecture, right? Because it's a hard-earned conjecture. Flip the sign and add 1. So that would mean actually that we do a bitwise flip. And this could be done, oh, sugar. In hardware, if we just had the ability to flip bits, right? If I had a circuit that allowed me to take a string and just flip it, and then I suppose this is 0, 0, 0, 0, 0, 0, 0, 1. Okay. So go ahead and flip those for me. 1, 1. Now let me ask you this. Did we figure out a problem on how to solve unsigned integers? Was there a space that we figured out where we could add unsigned integers in the past? I mean, we didn't actually do this in class, right? But the claim is if I constructed a data class to do unsigned integers, part of that construction was the addition problem, right? We actually spent some time on that at the beginning of this one. This right there, what type of problem is this? It's an addition of unsigned integers. So now I'm encoding negative integers using the same circuitry that I used to add unsigned integers, right? So now I've mapped the problem of encoding negatives to a bit component flip plus the addition of unsigned integers, which I've already done in the past. Right? No ifs, no else, no conditions. Very, very elegant. What's the corresponding encoding of this number? 1101, 1011. Let's go ahead and check that this is indeed legit. This would be negative 128 plus what? 64, 16. I'm not too good at this, but let's go see if we can take a look at what that is. That's going to look like 88, 90, 91. (91) plus negative 128. Have we proven our conjecture? We show that our conjecture works for a base case, right? Should we take a break? Or do you want to do some examples in Matlab? Some examples?
Sure.
Okay, maybe 5 more minutes, and then take a break. Let's do some examples in Matlab. What are you noticing? So I'm trying to set an example by actually doing what I do when I code. How much thinking goes into a single line of code? Yeah. To me, that's normal. To you, that might not be normal, right? I remember when my teachers would code, they'd code like 50 lines in a day, and it would all seem clear to them, and I'd be done with it, and I'm like, how do you know that stuff works, right?
Probably like 30 comments, 30 words of comments.
So let's do this. Let's go ahead and check. So let's do int 8 of 37. Let's go ahead and format short. So let's try again. Int 8 of 37. The value, the interpreted value of this number should be, I'm going to go ahead and format compact. We'll try again. So again, the interpreted value is 37. What did we say about the binary string? Zero, zero, 1, 0. So let's do this. Des to bin 37. And indeed, actually what we're doing is, this one would be 0, 0, 1, 0, 0, 1, 0, 1, right? Matlab, when it returned this, gave me a 6-bit string. Why did it give me a 6-bit string? Yeah, because it's giving me, it's literally converting it to the minimum number. Why am I adding the 2 zeros in my situation? Because I do need the 2 bits, because I have a data class that requires 8 bits, right? Okay, so let's think about what that is in hex. To 5, right? Okay, let's go ahead and check. Int 8 negative 37. What was our claim about the bit string for negative 37? Okay, let's do this in hex. Remember that this binary encoding is not a random unsigned integer. This is what we call the 2's complement. What's the corresponding value in hex? Well, this would be 8 plus 4 plus 1. 8 plus 4 plus 1 is 13. 13 is 3 minus f. F is 15. E is 14. D is 13. So what's that string right there? Should be D 8 plus 2 plus 1. So 9 A B. Yeah, that's base 16. So when we run this line of code, what do we expect Matlab to tell us? We expect Matlab to tell us that in memory, this number is encoded as so far, have we broken MATLAB's? Have we figured out whether or not the coders at MATLAB are full of malarkey or if they know what they're doing? So far. So far, they seem like they know what they're doing, right? Okay. How would we break it? What positive number could I put in? What's the smallest positive number that I could put in that would get me inaccurate data? (7F). What is that bit string? What number should that be? Should be 2 to the 7 minus 1. MATLAB is telling me that the current way that I've coded this up, 128 is equal to 2 to the 7 minus 1. What do we call that? Overflow. How would we fix overflow? Range extension. Okay, so we're going to do a little bit of proof at the end of today. Then we're going to state some theorems. And then we might actually get to a space where, yeah. Should we take a break here? Okay, let's take a break. When we come back, we'll finish up the last session in lesson 4. And then we might actually move on to lesson 5 today. We'll take a look at how that works. We'll see you in just a bit.